Alright, so let us move on to now shortest path based centrality matrix. So we'll begin with closeness. So closeness, as I said, basically captures how close is a vertex to the rest of the vertices in a graph. So that's what I mean by closeness centrality. Now, we did not do this for the eigenvector centrality. Now, if you want to measure the time complexity of this approach, okay, of finding the eigenvector centrality, um, you proceed in iterations, and in each iteration, what you do is multiplication. So you multiply each row in the adjacency matrix with the column vector, and you get the product vector and you normalize. So the multiplication is the key operation you repeatedly do. So from an algorithmic point of view, that's also called the basic operation that's repeatedly done. So in each iteration, you do v square multiplications because the matrix has v square entries where v is the number of vertices. So you do v square multiplications in each iteration. Now also the maximum number of iterations we would need, and actually the name of this method is called power iteration method. So that's the name of this algorithm, power iteration method or algorithm. So for this algorithm, the maximum number of iterations you would need is I think it is either the same as the number of vertices or one less than the number of vertices. I'm not sure, but we can say it is v iterations in the worst case. So it's v times v square, so that's going to be v cube. So that's the time complexity of the eigenvector centrality metric. To compute the eigenvector centrality metric, you have to spend this much time. So as you see, it's not really small. So for if a graph has v vertices, you're going to spend v cube time to compute it. So it's a computationally heavy metric, means it takes more time to compute. Okay, so that's why for very large graphs, so if you could try to run some large graph with the Java program I gave you, you may not be able to get the output because if you run it on say 100,000 or 10,000, probably 10,000 may run, but it may take longer time. But 100,000, I don't think it will run. So it's a very computationally intensive calculation because it is involving matrix multiplication. Alright, so now the closeness centrality metric is a measure of how close is a vertex to the rest of the vertices. So for that we need to get the distance matrix. And one way we can get the distance matrix is to use the breadth first search algorithm that we saw in module 1. And we already saw how to do this distance matrix later in another example when we calculate the average path length and all those stuff. So the same idea here. So for each vertex, find what's the length of the shortest path to every other vertex. That will be a distance. So for vertex 1, its distance to itself is 0, but to other vertices, so 2, 3, 4, 5 are all at a distance 1. Then 6 is at a distance 2, 7 is at a distance 3, 8 is at a distance 2. So that's the distance we can call it as a vector. Then for 2 again, distance to 1 is 1, to itself is 0, for 3 it is 2, for 4 it is 2, 5 it is 2, 6 it is 1, 7 it is 2, 8 it is 1. So for simple graphs like this, you don't really need to run breadth first search. You can just do like what I just went through. Just find the number of edges on the shortest path and get the distance. So once you get the distance vector, distance matrix, compute the sum of the distances in, actually that's called a vector. The row corresponding to a vertex can be called the distance vector for that vertex. So for vertex 1, the sum of the distances in the distance vector is 1 plus 1 plus 1 plus 1 plus 2 plus 3 plus 2, and that will add up to 5, 7, 11. Now vertex 2 also will add up to 11. Vertex 3, it will add up to 17 and so on. Vertex 7, it will add up to 21. So the sum of the distances is a measure of how close is a vertex to the rest of the vertices. So 1 is relatively closer to the rest of the vertices, so it has a lower sum for the distances. Similarly 2. Whereas look at vertex 7, it's very much in the periphery, so it's like somewhere out there at the one end. So it has to take a very the shortest path distances to the rest of the vertices for 7 is going to be much larger. So that's why we get 21 here, and these are the distance values. Now you could use the sum of the distances itself as a centrality metric, but due to the convention, and that's how even in the literature, in the research papers, people handle this. They want to maintain the convention that larger the centrality metric value, the higher rank is the vertex with respect to that metric. So you want to find or quantify how close is a vertex to the rest of the vertices. So we really want smaller distances, but we want to also maintain satisfies this definition. The larger the value, the higher rank the vertex. So that is why what we do is we take the inverse of the sum of the distances. So when you take the inverse, these are the values. So lower integer value, the larger is its inverse. Compared to say 21, its inverse is 0.0476, whereas for inverse for 11, it is 0.0909. So that will satisfy the definition that now larger the closeness centrality value for a vertex, the more closer is a vertex to the rest of the vertices. And that is now what we observe. 0.0909 is the largest centrality closeness centrality value for among all the vertices out here, and 0.0476 is very low. So we say that vertex is not closer that much to the rest of the vertices. Okay. Now the time complexity is going to be, you need to run breadth first search to find the distance vector for each vertex. So it is v plus e time complexity for running breadth first search once from a particular vertex. So you have to run it v times once for each vertex. So it's v times v plus e, so that is v square plus ve, or ve plus v square. So that is the time complexity for closeness centrality, and it is computationally intensive. As you see, it's v times e. E itself can be v square, so it is also kind of that of v cube. Okay, like eigenvector centrality. So that's not a good. It's not. I wouldn't say it's not good, but that's more computationally intensive. Okay, so what we'll now look at. So any question on closeness centrality?